So now the final presentation for this session is by David, and he's going to talk about solving string constraints with lengths by stabilization. And this is also a distinguished paper, so congratulations for that.
Just double displace works on the test and not here. Yeah, that's what I'm trying to do. Thank you for the introduction. My name is Chocholatý, and I would like to tell you today how we solve string constraints with lengths using stabilization. This is a joint work with Yu-Fang Chen from Academia Sinica in Taiwan. And I cannot move the presentation. Okay. For our motivation, we focus on a high demand of SMTs and string solvers, especially in the industry. In the industry, it is important to be able to reason about strings, for they are used for analysis of programs and manipulations of strings in programs, or for prevention attacks such as cross-site scripting or SQL injection. And one example to speak for them all could be how Amazon in Amazon Web Services uses a whole portfolio of several SMT solvers where they run this portfolio of SMT solvers simultaneously on a whole, as they say, 1 billion SMT queries each day. And for each query, then run this portfolio simultaneously. And whichever SMT solver finishes first, its result they take as a satisfiable, unsatisfiable for some string constraint. As you can see, there is a wide range of string solvers, Z3, CVC5, or derivatives of these string solvers, such as Z3 Trau or Z3 string 3RE, or separate ones such as ostrich. So take a look at this example string formula. What we can see here is that there are equations and disequations. There are regular constraints, which talk about variables in the equations and disequations. There are length constraints, again, talking about lengths of some variables in the equations and disequations. Or there can be also some other more complex string operations and constraints, such as substring or contains. So how can we solve this string formula with these constraints? Our approach is to use a combination of two automata-based algorithms. The first algorithm is called stabilization. It's a novel approach where we tightly integrate equations with regular constraints. It is a fast approach, and it can easily solve equations with regular constraints, but due to how the algorithm works, it cannot solve length constraints. But we can and we want to solve length constraints. Therefore, we combine this algorithm with another older approach called align and split, which is a slower approach, but can solve length constraints. Furthermore, we expand this combined approach to be able to solve these equations and other string constraints which expand the formula or a part which can be solved to the whole formula which we saw earlier. So for the first algorithm, align and split can solve length formulas with equations and regular constraints, where we have an equation and each variable in the equation has assigned some regular language. And somewhere in the constraint formula, there is a length constraint, such as the length constraint at the end for variable x. First, we do a full equation alignment, where we align the left-hand side of the equation and the right-hand side above each other. And we try to see where are the borders, or relative borders of each of the variables. So for example, the variable x can either be inside u, or inside v, or inside w. And we get these case splits. So for the first case split, the variable x has a border inside w. Each of the case splits need to be handled separately. Note that we generated here 6 case splits. That's too much to use this algorithm alone, therefore the combination. But for the first case split that is generated here, we note this equation alignment with substitutions which we append to the formula, and and then with operation on automata. Remember, each of these variables is represented in our approach as a automaton, finite automaton. Therefore, we can do some automata splitting and compute this formula into a pure regular constraint formula, which contains only regular constraints. The equations are eliminated thanks to the automata splitting. And thanks to the monady decomposition, this gives us possibility to extract lengths from these regular constraints. There are regular constraints represented by automata, and from each automaton for each variable, we can extract some regular length constraints, which we then append with the length constraints in the input formula. And what we get is a new length formula, which we can pass to SMT LIA solver. LIA stands for linear integer arithmetic, which will give us an answer for satisfiable or unsatisfiable. The second approach is stabilization. Stabilization is our novel approach, which is really fast for equations and regular constraints, but it cannot solve length constraints because there is no monadic decomposition, so no length extraction. But there are no splits, as in the equation alignment splits, and no new variables are introduced, such as the subparts of the variables which were introduced in the equation alignment. We concatenate the languages for each of the sites in the equation. One with a special delimiter, that's the pound symbol, and the other normal concatenation, again in types of automata. And then do automata product construction, which we modified in a smart way to be able to refine languages for each of the variables. Once we refine these languages, we can simply check whether some of the languages is empty. If it is empty, the formula is unsatisfiable. If all of them are refined and non-empty, then the formula is satisfiable. If we combine this algorithm, we want to use stabilization, which is fast, for all of the parts in the formula which only talk about regular constraints and equations, but not about lengths. If we have lengths, we have to use the align and split method. Therefore, we do only a partial equation alignment. We again align left-hand side, right-hand side of the equation above each other, reason about where the possible borders of the variables can be. But now we reason only about the possible borders of the length variables. That's x in this case. Y and z can be considered as a single variable for the purpose of this partial equation alignment. Notice that the case splits here are only 3 instead of 6. That's the improvement that we've made. Then each of the case splits needs to be again solved separately, but we can split the problem for each split into sub-problems. One for the length part, which can be solved easily by align and split, thanks to monadic decomposition, and the non-length part, let's say, which can be solved even more easily thanks to stabilization, because there are no lengths now. The lengths have been extracted only to this left part in this case split. And the same goes for the other splits. Then we took this approach combined and we extended it even further. We extended it with string constraints, which can be solved easily by rewriting them into more simple constraints, and by saturation of basic constraints, the performance increases. Also, we added support for unrestricted these equations, again by eliminating them and rewriting them into another form of length formula, which can be solved by SMT Elia solver. And we get an algorithm which is complete on the chain-free fragment, and even extend it further with unrestricted these equations, which gives us a new largest known fragment, decidable fragment, which contains equations and unrestricted equations, regular constraints, and length constraints. We implemented this approach in Z3 Noodler, which is based on top of Z3, and it replaces this theory of strings. Our solver is a string solver, so it replaces this theory of strings and some other parts of Z3. Then for our approaches, we need automata, finite automata and quick operations on them. For that, we implemented our own automata library Mata, which handles the representation of automata and operations on them. What we get is a very fast and string solver, which is complementary to state-of-the-art string solvers used in the industry. As you can see in the examples, in the first table, we have taken benchmarks from praxis, from real problems, which are part of SMT lib, and we've split them into 3 groups. One is for regex heavy benchmarks, one is for equations heavy benchmarks, and one is for benchmarks which are heavy with predicates or predicate uses. As you can see, Z3 Noodler performs well on mostly all of these. It has the least number of unsolved instances for a large number of benchmarks, or at least it's close to the best string solvers for the given benchmark. In the second table, we can also see that the average runtimes of the Noodler are the lowest for the first 2 groups of benchmarks. If we take a look at a comparison in these scatter graphs with Z3 and CVC5, we can easily see the 90-degree axis here in the graph and here, which shows us that the Z3 Noodler is complementary to both CVC5 and Z3. If CVC5 and Z3 cannot solve it, we can solve it really fast, as opposed to what CVC5 and Z3 has to do, has to compute. If we take a look at what the first example I gave for Amazon Web Services, we take a portfolio of several SMT solvers, run them together, and compare them with the performance of zNoodler in this kettle prot. We can again see that Z3 Noodler is complementary to the whole portfolio. And even in the Cactus plots, we can see that Z3 does really well on its own. That's the green line. But if we combine Z3 here and here, but if we combine Z3 Noodler only with, for example, CVC5, we get basically the same performance as we would get if we run all of these 7 SMT solvers together simultaneously. So instead of 7 SMT solvers, we have to run only 2, Z3 Noodler and CVC5, and we get basically the same performance and solve the same number of instances. This can be easily seen in the table, where if we take the virtual best solver and remove Z3 Noodler here and here, the performance increases drastically, and also the number of unsolved instances increases. So to conclude the presentation, I've talked about our approach, which combines 2 algorithms. One of stabilization to easily and quickly solve string constraints with equations which are tightly integrated together, and a line and split approach, which solves equations with lengths. Also, we implemented this approach in new string solver, which uses as an underlying library for handling of automata our library Mata. And right now, as Z3 Noodle and both with Mata are ongoing projects, we work on supporting string constraints, other string constraints, adding support for transducers, and also to generate witnesses or certificates. This would be all for my talk, and now there is a place for questions, I believe, and thank you for your attention.
Questions?
So thanks for the talk. So I have like some functionality question about, so is this decision procedure can apply to some string operations like reverse, lower, upper case?
We can also reason about these constraints, but currently we support only constraints which appear in the SMT string theory specification. So for example, substring, index of, contains, and this kind. For example, to upper, I believe is not in the SMT.
So the point is that you haven't tried these.
We haven't tried these. Okay. We don't have benchmark for these. And frankly, the approach would be to take, or create some benchmark with these constraints and rewrite these difficult string constraints to some form of easily solvable constraints which contain length constraints, equations or disequations, and regular constraints again.
Yeah, but I think a follow-up question is I think in real world we have so many like unbounded strings. For example, I think one problem I could think of is, let's imagine you have a string S which matches A plus. Okay. And we know that S reverse is equal to S itself, and we want to prove this theorem using SMT solver, which means you want to check the negation is unsatisfiable. So do you think this kind of problem can be solved in this framework?
I believe that yes, it can be solved. Again, as I said, we can rewrite this constraint into some kind that, for example, the reverse of a string has the same length as the original string, and the index of the first symbol in the string is at the index of the last symbol of the reverse string.
Yeah, but since this S is unbounded, so how can you specify the last index of a string? Because it can be infinitely long. So do you think that will also apply in this case?
I believe that, yeah, it would apply because you would just create a harder constraint which would tell that the index is length of the string -1, for example. That's that's the specification of the problem in formula.
Yeah, thank you.
Hi, I'm Pratik. I'm from NUS. Excellent work. I just have a very short question. So do you support word equations as part of the theory or not?
Word equations?
Yeah.
Yeah, we support word equations.
They're all part of, and the whole subset that you have right now is still completely decidable.
Yeah, it is decidable.
Okay, thanks.
All right, let's thank the speaker one more time.